Hi, so I'm Lexi Doherty, and I'm about to go over the von Neumann stability analysis for the finite differencing equation. So what we were just looking at was this equation, the finite differencing equation. It is Tj to the n plus 1 equals T sub j to the nth power plus the rate times T sub j minus 1 to the nth power minus 2 T sub j to the nth power and plus T sub j plus 1 to the nth power. And so some of these equations that we're going to look at are going to prove why the rate cannot go outside of 0.5 and just why the graph started to get all wonky, and just really showing the limits of how the rate can be calculated and everything with that. So I just want to point out that Euler's equations, these are just some equations that we're going to be using to substitute and just simplify our equation. And then this was the graph that was shown, shows the initial condition and then the final condition. It was just similar to the code where we were just looking at, and then the Fourier series, which is going to equal a whole summation, and it just gives us a little bit more of an insight to the overall problem. Something that we're going to begin with is using these calculations from the Fourier series. We're going to find that t to the j plus 1, or t sub j plus 1 equals e to the I k delta x, and then t with j minus 1 equals e to the negative I k delta x. And we are just going to go right on ahead and substitute those into the finite differencing equation. So with that, let's get started. So that's going to be the rate times e to the negative I k delta x minus, and then we are just going to put this at 2tj, so we're not changing anything. So 2tj n, oops, and so there we go with that. And I'll close out this parenthesis, and as it is shown here in the Euler's equation, we actually find that 2 cosine of kx is going to equal e to the I kx plus e to the negative I k delta x, which is what we have exactly right here. So if I rearrange that as well, we're going to get tj n plus 1 and then 2 cosine kx minus 2tj to the n. So, my knee just popped. So there we have just a simplified version so far, and we're going to use that and work a little bit more to try and derive this. So what we're going to do first is just kind of move around the equation so that the TJs are not in the way, and we're just going to more or less eliminate all of that. And we're going to start by pulling out this TJ, and I'll rewrite the equation. So it's going to be TJ plus 1 equals tj, and then 1 plus r times 2 cosine kx minus 2, and minus 2. So we'll close all of that out and start working with that. And if we pull out the TJ, so we're going to find out that this is actually equal to, this has to be less than 1. And we're getting that by taking the absolute value of the inside of all of this and tjn, and this tj to the n plus 1 is going to equal tj to the n plus tj. And when we substitute all of that out, it's going to have to equal less than 1. And so when we start looking at this inside piece, so this inside piece is definitely going to be the most important as we're working along all of this. So what we're going to start with is 1 plus r 2 cosine k of x is less than, or minus 2 is less than 1. And we're going to change that around so that it is negative 2 is less than r times 2 cosine kx minus 2 is less than 0. So see how we took the absolute value, so the absolute value is less than 1, so if we take away the absolute value, then it is going to have to be between 0, or negative 1, 0, and then 0 and 1. So that's just imagining, so there's a negative 1 on this side, 1 on this side, and then if we pull out this 1 right here, we can change this into 0 and negative 2. So that's just laws of inequality, so we can work with that and kind of keep all of that going. And so after this, we're going to do pulling out this. Sorry, some technical difficulties with my computer, but we're back to not having an orange screen. And so what we're going to do here is we're going to pull out 1 of this negative 2, and we're going to move that to this side and add that over so that our new inequality is going to be negative 1 is less than r times 2 cosine kx minus 1 less than 0. And so that's just going to stay within that domain. And what we know about cosine is that is a sinusoidal function that always oscillates between, it's always going to oscillate, forgot to take out that 2. So since we divided out a 2 here, so we said it's 2 outside of the parentheses because we can't subtract anything that the r is impacting. So once we take out the 2, then we're able to subtract it out onto the other side. And so anyway, so back to the cosine. So what we know about cosine is it's a sinusoidal function that is going to oscillate between negative 1 and 1. And it will never exceed those unless there is a function outside of it that's going to cause it to increase and decrease. But in this case, it's always oscillating between negative 1 and 1. So in order to maximize the radius for this test, what we know about cosine is that in order to maximize what's inside this parentheses, we can write that as negative 1. So after doing a little bit of flipping, what we're going to get to is that negative 1 is less than r times negative 2, which is less than 0. So r times negative 2 is going to follow within 0 and negative 1. So what we're going to do is divide out the negative 2 on either side so that we can get to negative 1 over negative 2 is less than r, which is less than 0. So if we add all that out, we know that r has to fall within 0 and 1/2 in order to keep a steady state equation, which is exactly why once we saw when the radius was higher than 0.5, why we started to see some turbulence in the graph and just everything started to get kind of wonky. That's just because it's outside of the limits according to the von Neumann stability analysis, which is just plugging in Euler's equation and just doing some substitution and just really getting in depth into the finite differencing equation.